All right, I think we'll just kick it off. All right, welcome everyone to the Understanding Latency webinar series. My name is Björn Ivar Teigen. I'm head of research at Domos, and I'll be your host this morning, afternoon, evening, depending on where you are. So we've been looking forward to this event for a long time and are very excited about it. The speaker lineup is truly excellent. And frankly, we're a bit blown away by the amount of interest that this has generated. Now, first, let me get some practical details out of the way. So we'll have 3 types of sessions during the webinar. So each day kicks off with a keynote talk, followed by a series of panel discussions and talks. So panel discussions will be roughly half an hour, and each talk is 15 minutes. After each keynote, talk, and panel, we'll do a Q&A. So we invite everyone to ask questions. And to ask a question, please use the built-in Q&A system, which you'll find at the bottom of your screen. And do note that the webinar is being recorded, so any questions you ask will be part of that recording as well. Okay, so before we start, I'd like to talk a little bit about how this came together and why we're doing a webinar series about latency. Latency is a crucial and underappreciated part of creating good user experiences on the internet. It's underappreciated with customers or end users, if you like, in particular, but it's also underappreciated in the industry. And that's why we wanted to create a stage for the people in our industry who are banging the latency matters drum. And some of the speakers have been working on this for literally decades. And the lineup covers all major parts of the internet industry, including Linux kernel developers, infrastructure vendors, internet service providers, and user-facing applications. And I think it's pretty cool that it's possible to gather such a diverse crowd around a single topic, which just goes to show how important latency really is, and that it's something that affects and is affected by the whole technology stack. This event will be a knowledge sharing event. The point is to share experience, insights, and best practices related to measuring and improving latency. So this is about highlighting a problem space or opportunity space, if you're the optimistic type, that all of us have a shared interest in tackling together in the best way possible. So with that in mind, I'd like to introduce the program. The webinar spans 3 days, so it's Monday, Tuesday, Wednesday. The Monday, today, the topic is what is latency and why does it matter to you? Tomorrow, Tuesday, we will cover how big is the problem and what's being done to fix it. So we'll have speakers talking about how to measure latency, actual results from measuring latency at scale, and various people working on solutions for the latency problem. Then finally on Wednesday, we'll be talking about commercialization and deployment of solutions. So stay tuned for that. Today, the topic is what is latency and why does it matter to you? We'll have 5 sessions. First a keynote, then a panel, followed by a 10-minute break. So if you want to get more coffee or something, please use the break for that. And after the break, we'll have another panel and then 2 more 15-minute talks. So with that, I'd like to introduce our first keynote speaker, Gavin Young from Vodafone. Gavin is head of Fixed Access Center of Excellence at Vodafone Group and has been pushing the industry towards a latency-centric point of view for a decade now through his work in Broadband Forum, Cable Labs, and Vodafone. So please, Gavin, take the stage.
Okay, thank you, Bourne. Let's just see if I can share my screen. Can you tell me if you can see that okay?
Not yet.
Did you stop sharing it your
I did,
side?
yes.
Okay. That come through yet?
No.
Okay, let's try this once more.
There we are. Now something's happening here.
Right, there we got there. Bit of latency there, just to
Very
make a
good.
point.
All right,
Right,
take
thank
it
you so
away.
much, Bjorn. Thank you, and I'm very honoured and privileged to be able to kick off this series of 3 days of discussion around latency. And the challenge Bjorn has set me is to explain why the time is right to fix latency. So hopefully in the next 15 minutes, I can try and convince you of that. So if you look at our broadband industry, it's been characterized up till now by the last kind of 20 years or so work focusing on the quest for speed to make broadband internet access faster and faster. And we have a whole range of technologies to help us there. And we're now at the point we're selling gigabit connections to customers. Then some operators have gone beyond a gig, and there are a number of physical layer technologies, shall we say, that enable us to deliver multi-gig. We have DOCSIS 4, 10 gig XGS-PON, 25 gig, 50 gig, 100 gig PON, coherent PON on the horizon. And within the home, we have Wi-Fi 7 that should be coming along towards the end of this year, early next year. So a whole range of technologies that are designed to solve what I'd call the signal to noise ratio problem, which is about increase in peak speed, increase in capacity. But the challenge is speed is only one dimension of the broadband network performance and the implications of that for customer experience. So speed is necessary. You need a minimum rate to get through an ultra high definition video stream. It's necessary, but it's not sufficient on its own to deliver excellent quality of outcomes, shall we say, of customers' applications. So really, as broadband or network engineers, I think we need to set our sights higher and look beyond speed and try and have a higher level vision of what we're trying to achieve with these networks. And I think what we need to try and do is not deploy the fastest network, but to actually have aspirations to make that network invisible to customers, so that the customer doesn't detect that there's a network between their smartphone, their smart TV, their laptop, and the application or the content server that they're trying to access. And if that network can give the impression of not being there, so that it always provides the right resources to give sufficient outcome for excellent application outcomes every time they use it, no matter what time of day, then at that point maybe we can say we've done our job and the network truly is invisible to the customer. And we need to look ahead, because applications are evolving. Today, a lot of traffic is on the network is dominated by streaming video, but there's a whole bunch of other apps that folks are working on, and some of these may or may not get traction. Some may become mass consumer, some may not. But one of the things that characterizes a number of these new applications is they're about increased collaboration, interactivity, and response time. So whether that's holographic technology for virtual presence, HoloLens, AR, VR, gaming, immersive experiences, remote musicians collaborating, education using VR, and haptic feedback applications. A lot of these require much more responsiveness of the network. So we need to try and anticipate what we'll need in the next 5 to 10 years, given the lead time that it takes to build new infrastructure. And so, to put it bluntly, we need to create a more tactile internet, and we need to factor in, human physiology and response times, where any humans are going to be interacting with the network, so that the human being in the loop becomes the bottleneck, the limiting factor, and not the network itself. Now, granted, there will be, a number of requirements on the network, even more onerous than this, where perhaps we have machine-to-machine communication and response times there. So that in itself is another set of requirements. But as far as human interaction with the network and some of these collaboration applications, we want to remove the network as being the bottleneck. And really, apart from making the network look invisible, we've got to do that in a way. We've got to get this right so we don't, for example, make our customers feel motion sickness and things like that with some of these new virtual reality applications. And these are now coming to the fore now. And the benefits of reducing latency in the network, it goes beyond just improving the application outcome per se. There are other benefits to the wider ecosystem and commercialization of these new generation of services. So, for example, if we take virtual reality and these kind of metaverse-like applications, the head-mounted display, the HMD, that has three challenges, that are potential barriers to this becoming a mass market. So one is the weight. After a few hours of one of these on your head, I've got one myself. It does start to strain a bit. Another is battery life. It might last 2 or 3 hours today. And the other one is cost, of course. These things aren't cheap. But that can also be addressed by reducing latency in the network by offloading some of this kind of processing from the headset itself onto the edge of the network. But in order for that to work, we do need low latency, and then we can reduce the weight, increase the battery life, reduce the cost, and maybe that will help a more mass market adoption of these kind of services. So there are peripheral benefits rather than purely the application outcome itself. And so it could help stimulate that wider ecosystem. So if we look at the broadband industry today, this is trying to put our business model, if you like, on a page. If we start at the bottom left-hand side, as network operators, we invest money in building networks today. Typically, that money is used to increase bandwidth over time, the bandwidth, the speed we offer to customers. And the customer, for their part, if they want to see whether they've got what they paid for, most often today, they would do a speed test. And then if they get the outcome they expect, then hopefully we get a good net promoter score, the NPS there. And if we have a happy customer, we can upsell them to other services. We can increase the average revenue per user. If we get that process wrong, of course, we get support calls and churn. And up till now, there's been quite a good coupling between these kind of different facets here in the three layers. As we've increased speed, that has reduced the web page load time, noticeable benefit to the customer. It's also enabled customers to go from standard definition video to high definition video to 4K video streams. And so that there's been a benefit. But the challenge we have today is now we're selling 1 gigabit. To be honest, there are hardly any customers that burst beyond 200 megabits or so, unless they're doing a speed test or they're doing a big software download, in which case that's non-interactive. And if they have to wait a minute or two more, it's probably not a big deal. So being in a business where you have to invest a lot of CapEx to increase the speed, and we're in diminishing returns here, a customer's 4K video stream is not going to look any better on a 2 gig connection than it does on a 1 gig connection. So that's not a great business to be in. So we've kind of squeezed everything we can out of the perceivable benefits of increasing speed, and we need to look at these other dimensions of quality of experience. And of course, latency is an absolutely key one, particularly when we think about some of the newer applications that I mentioned earlier. So we need to get the industry away from this one-dimensional focus on speed and bandwidth. And of course, not all bandwidth is created equal, although some people talk about it as if it was. So 50 megabits on an empty network is not the same as 50 megabits per second on a loaded network due to queuing and buffering. It depends on the load on the network. And similarly, 50 megabits on a 100 meg Ethernet port is not the same as 50 megabits per second on a 10 gig port because of the different serialization delay of clocking packets in and out, which is the same reason why 1/10 of 100 megabits is not the same as 10 megabits per second because of the port speed. And finally, the physical layer performance of the different technologies at our disposal, they vary quite a lot as well. So 50 megabits per second on a DOCSIS 3.1 network may have different characteristics than 50 megabits on a 4G or a GPON network. So really, this use of bandwidth as a proxy for application outcomes for goodness is, it's a weak proxy, and it has limitations. If we look at the fixed broadband, the digital supply chain, as we go from an application server all the way down to the customer, the end user's device, increasing the broadband access speed only affects one hop in that link, and the customer's experience of their application or the content is obviously impacted by all the hops in that supply chain from server to device. And that's, as packets traverse that network, they degrade over time, and they're impacted by, it could be Wi-Fi congestion or home router performance, capacity, rerouting, interconnect issues, and even in this modern kind of cloud era of applications moving between servers and even between data centers. So as engineers, we're used to degradation of quality accumulating as we traverse networks. So electrical signals attenuate, optical signals attenuate, radio signals attenuate. And at the packet layer, that degradation is an accumulation of latency at every hop. And some of those packets may even get dropped as well. So it could be an accumulation of latency and some packet drops. So that's the attenuation of quality at the packet layer. So the perfect network would have zero delay and zero loss, but reality is every packet will get delayed by a finite amount, and some will experience loss. But if we can measure latency and really understand what's happening on those hops, both upstream and downstream across those links, then we can get insight into root causes of issues. And some of the phenomena we've observed with various latency measurements include rerouting, load balancing, packet fragmentation, interleaving and profile changes in different technologies, processor overload, misconfigured schedulers. That's a really tough one to find with normal NOC tools, but with the right measurements, you can identify these things. But also to see the benefit of quality of service approaches, the impact of different technology and architecture upgrades, and radio bearer changes. So, there are different categories of things here. There's the physical layer, the route or the path that's been taken, and the load on the network as well. So one of the key questions to ask ourselves is, how can I get from a latency measurement to some of these root causes to help me optimize my customer experience on the network? So what we really need to do is get a lot more surgical about how we measure latency. Today we've had minimum, average, and max round trip times for a while, looking at latency, but really what we need to do is try and deconstruct that latency a little bit more, have a higher fidelity approach, a kind of X-ray into what's inside, what are the components that make up the latency, and then how do we link those latency measurements to the application outcomes and the customer quality of experience. And we'll be hearing a bit more in the next 3 days around some of the approaches that can be taken to do that. And really, this is a question of treating the network illness, if you like, if there is a problem, with the right cure. And we're only going to get that right if we really understand some of the components of latency. So, for example, if we have a kind of queuing and buffering challenges because of network load and congestion issues, then that's the sort of thing we want to look at, improving the scheduling. And there's a whole bunch of technologies and techniques there. Windows Wi-Fi multimedia, hierarchical QoS, low latency DOCSIS, L4S, etc. We'll hear about some of these over the next few days. If the source of the problem is serialization delay and link speeds, well, we can increase the link speed. Although I should point out, in a modern, well-engineered broadband network, the serialization delay component is often the smallest. It can be an order of magnitude smaller. And finally, there may be fundamental limits due to the physical distance and the speed of light because of the topology of the network itself. So in order to overcome those things, we have to look at moving content or processing closer to the customer with techniques like MEC or cache or CDN. And maybe one day there might even be the chance to optimize, routing and by using hollow core fiber, for example, to affect the speed of light on the particular physical media. So
Gavin,
understanding.
sorry to jump in, Gavin. You might not realize you have the Zoomer sharing your screen message floating above the slides, and it's
Oh,
obscuring
right.
the slides.
Hi, there we go. Thank you. Thank you for pointing that out. Thank you. Um, yeah, so really, we want to understand the components that make up the latency in both directions, and this will then enable us to focus our capex and our resources on the best fix to optimize the end-to-end performance and hence the user experience. And this is something that I've kind of talked about this as if it's an in-life issue. We got networks they're suboptimal. We want to find root causes of an in-life network. And yes, we can do that. That's the top right of this picture here, network health checks, root cause analysis, that kind of thing. But the ability to measure and understand latency is something that's useful at all phases of the life cycle as we go from concept to customer deployment. So working our way back, we might have, SLAs for enterprise and wholesale customers. Maybe we can use this to compare the advantages of deploying a MEC or a cache or not, because things like MEC are not cheap to deploy. You need to find space and power. What benefit are you going to get to that? Can you measure it? Can you model it? Can we, optimize scheduler performance? And at the moment, our industry is going through a transition where we're building networks less from physical boxes, monolithic boxes, and more building them with software and virtual network functions and containerized network functions. So we can use latency measurement to compare and contrast different technologies, but also different vendors. They're going to build things in different ways. And also in the lab, we can do kind of A/B testing. We can emulate latency and see the impact of a certain network or technology setup on applications, and really kind of characterize different technologies. So a whole range of applicability at all phases of the life cycle there. But the good news is there's been a lot of collaborative standards activity and complementary, should I say, in this area. So if we look at latency measurement, Cable Labs has been doing a comprehensive analysis of all different latency measurement techniques and looking at metrics and architectures. Broadband Forum has done a lot of good work around quality attenuation measurements using active test protocols and including the architecture and the requirements in that space. And the IETF has standardized the simple two-way active measurement protocol, or STAMP. But it's one thing to measure it, but we want to mitigate latency as well. So in that space, Cable Labs has had active queue management for a while in the DOCSIS technologies, and more recently low latency DOCSIS. Broadband Forum has done work on hierarchical QoS and sort of functions you have in BNG and edge routers or even access nodes. And the IETF is doing some great work around L4S, low loss, low latency, scalable kind of throughput techniques there. So some really good work from those three bodies, and there's probably a lot of other stuff I haven't covered there, but just to give an example. So in summary, why do I think the time is right to fix latency? Well, I think we've largely solved the signal to noise ratio problem of speed and capacity. We have a whole array of technologies we can bring to bear on that. We know how to do it. We can't always afford to do it everywhere we'd like, but that's a kind of separate issue. But we know how to move towards the multi-gigabit era, which, to be honest, is beyond what many users actually need today. And so just focusing on increasing speed, that's now got diminishing customer perceived benefits in this gigabit era. And a new generation of applications is coming along, which will require a more tactile and responsive internet. So the next frontier, and I truly believe this, is to optimize the packet layer performance, especially latency. But to optimize it, you need to measure it. And this is where we now have some good set of standardized tools to do this around measurement and optimization. But we're also, as I alluded to earlier, we're at an inflection point in our industry. We're no longer, as network operators, in the business of building a telco network or a cable network. we're really in the business of distributed computing. We have the move to cloud, virtualization, containerization, MEC disaggregation, control user plane separation, and a whole host of telemetry and analytics that can enable us to use machine learning and AI and closed loop automation and all this good stuff. So we're going to have, compute capability, in different parts of the network, in that end-to-end distribution chain. We're going to be moving functions around. But to be honest, there are 1,000 ways of getting this wrong if we don't understand latency. So just to wrap up with, yes, we've made great progress in standards. There's a lot of great tools and techniques out there. We'll hear a lot about them the next 3 days. But I've also got a wish list of things to think about that I think as an industry will help us, take things to the next level. So if we look at applications, they all have different latency requirements and so on. There was a very old technical recommendation, TR126, that was published in 2006. That in the days of triple play services, and that cited the latency requirements of a number of applications. But that was 2006. Things have moved on since then, and I think there's an opportunity to reevaluate the latency requirements of applications and classes of applications, and maybe express that in the form of QTAs, as quantitative timeliness agreements. I think we might be hearing about that in the next couple of days as well. And that enables us to combine latency and packet loss in a kind of single way of capturing that. Another thing I think would be useful was a rogues gallery, if you like, of latency measurements where something's gone wrong and the known causes. When you measure latency, and you can display this in different ways, but packet fragmentation and buffer overload, traffic rerouting and profile changes, these create specific kind of characteristics and things that once you've looked at this for a while, you recognize the patterns. But if we build up this kind of portfolio, if you like, of this is what it looked like and this was the root cause, then maybe that could help machine learning, training and closed loop automation to really identify these root causes more expediently. I think STAMP and quality attenuation, these kind of tools, I think if we have interoperability certification and maybe even open source variants of that could help drive things forward. And finally, L4S, which we're going to hear about a bit more, I think that's got huge potential. But again, certification and interoperability around that could be useful as well. So that's just a few personal thoughts around gaps that maybe we could fill. So really, I'm hopefully I've convinced you that I think latency and stationarity around that is the new speed. We've done a great job on speed. We know how to solve the signal to noise ratio problem, but we need to put much more focus on latency and how we manage it and how we mitigate it. Okay, thank you for your attention.
Thank you very much, Gavin. We don't have time for many questions, but there is one here. Satish is asking, is the distributed nature of the deployment introducing more latency?
Potentially, if you distribute things and more functions in there, you've got more elements where packets have to be clocked in and clocked out. So if you get that wrong, you can do it, although that serialization delay tends to be a smaller component. But I think, as we move to virtualization, as typically as part of this moving compute around, you get into issues around NIC limitations and whether things are running in kernel, non-kernel, and what shared resources and this kind of thing. As I said, there are 1,000 ways of getting this wrong. So it doesn't have to, but it can easily mess things up if we don't pay enough attention to it.
Right, thanks. With that, I think we're moving to the next panel. So that will be moderated by my colleague Magnus Olden. So Magnus, if you'd like to step in.
Yes, hello everyone. Thanks for coming and thanks to all the panelists. So we have a panel now on causes of latency. And with me today, I have my colleague, Björn Teigen, who you have seen a lot of. He's the head of research at Domus. He just finished a PhD on latency on Wi-Fi. And Björn, do you want to elaborate a bit more about you?
Yes, yeah. Hello. I run research at Domos. We supply internet service providers with measurement software and insights into the quality of their networks. Gavin, you need to stop your screen sharing, by the way. Thanks.
Okay, so that was Björn. I'll go directly to Brennan Smith. Brennan, you're VP of Technology in Ookla. I heard you do a bit of network testing.
We do a little bit of it. We've been doing it for a little while. So thanks, Magnus. My name is Brennan Smith, VP of Technology at Ookla. Many of you know us as the company behind Speedtest, but we're also the company behind Down Detector and a few other consumer products. But we are also one of the main producers of enterprise data for network operators, MNOs, et cetera, to be able to understand everything from overall coverage all the way to consumer sentiment. Our goal is always to improving connectivity for everyone around the globe. Latency, and specifically loaded latency, a lot of what Dave has worked on was what brought me to Ookla over a decade ago. So it's fantastic to finally see this really hitting its stride in the industry, and I'm so excited to be part of helping make it important into consumers' minds.
Okay, Dave Toth. I just added you as buffer bloat legend and writer of many things, but you can introduce yourself.
Hi, I'm Dave Toth. I've been involved in the internet since the early 80s, and my dream, starting from the very beginning, was to make it be able to play for musicians to collaborate together over the internet. And it's taken a really long time to get there. So I co-founded the Buffer Bloat project with Jim Geddes in 2011 because my network in Nicaragua failed when it rained. I had 30 seconds of latency I hit. Didn't understand why. Started poking on it. And along the way, we have discovered and built so many wonderful algorithms like FQCoddle and Cake and so on, and fixed zillions of routers that consumers can get today along the way. And these days I have been working on, I've moved up the stack. I'm working at the virtualization layer at coming up with ways of building better middle boxes that can manage latency at the ISP later as part of LibreQoS.
Very cool. And I know everyone is thinking this. So Dave, where are you?
I'm on a sailboat in Half Moon Bay, and I'm talking to you live via satellite. This is over a Starlink terminal, and it's just so amazing that I can do that today. I started when we had little 300 baud modems, and it's really great that we can do this worldwide.
Very cool. Okay, the panel is called "What Causes Latency?" Who wants to kick it off?
Well, I can start with the very simplest thing that causes latency, and that's distance. If you're a certain distance away from something, the speed of light limits how quickly you can communicate with that thing. And in the internet, that actually matters. The time it takes to go around the Earth at the speed of light is 133 milliseconds or thereabouts. And that's about the time it takes to blink, which is not that long, but it's actually noticeable. And when we have lots of round trips to do things, then that really adds up and matters.
Yeah, Brennan, you're eager. I'll give it to you.
Yeah, no, I mean, you brought up a perfect point there, which is, for us to be able to do many things on the internet. People talk about latency. It drives me nuts whenever this happens. It's like, oh, latency, it's gaming. It's a fast twitch medium. Anytime that there's something that's synchronous in the human mind, that's what people associate latency with, which is unfortunate because I think, most everyone on this talk knows is it governs the majority of most experiences. If you're doing DNS, TCP, and TLS, like you already have many round trips. Well, that 133 milliseconds that you were just mentioning, Bjorn, now is 500 milliseconds, 600 milliseconds. Now that just ruins a web page loading. So it's how do we bring that forward to the consumer face to be able to say like, no. Latency is not just gaming. It's so much more and foundational to how the internet works for everyone.
I think we all agree there. Dave, do you want to follow?
Well, I go back to my musical analogy. If you see a band on stage, you see them not much further than 8 feet apart. It's 8 milliseconds. A foot equals a millisecond. And it's really, really difficult for a group of people to collaborate at distance further than that. It's really hard to make good music. And the quality of a conversation changes if you can be whispering into someone's ear or shouting across the boat. And as we increase the intimacy of the internet by reducing round trip times, I'm hoping that our ability to respond to nuance improves in particular.
Yes, you can even see people at this panel are starting to talk over each other. I'm looking at you, Björn and Ben, so hopefully we can do that better. Okay, so but Björn kicked us off with what causes latency is distance. Dave, I think you worked a bit with queuing and something called buffer bloat. Could you explain what that is?
Okay, so I have a funny demo of this. So when we developed the internet, we cared about single packet serialization delay. And we also needed, because of the varying technologies that we had to apply a little buffering to how we transmitted data. And as we added more and more data, we just added more and more buffering, which meant that the amount of jitter that you experience when you actually use the internet can really grow. But we didn't care, and we just kept adding more, and therefore a web page download and stuff. And by the time that I got involved in this, it had grown to seconds or tens of seconds. We have results showing hundreds of seconds for certain technologies, and managing queue delay turns out to be a really difficult problem. I have a demo. This is live, so forgive me if this goes wrong. So instead of figuring out methods to control the queuing delay, we just added more and more buffering and killing the latency of the network. So this is an example. This is a funnel, okay, buffer bloat funnel. And we pour more data into that. And there's only this much data coming out. And then by the time it overflows, the signal back to the sender says, oh, I should slow down. But during this period, while this buffer is draining, my conversation with you today would be stopped by seconds, sometimes minutes. And this is the root of the buffer bloat problem, is that building better adapters, more awareness of the applications between here and there, will let us have this flow from the servers up here come out at this speed with a much tinier buffer and queuing delay. And that's been the focus of my work and the work of so many here for so many years.
It's a very, very good demo. So now we covered distances, buffering. Is there anything else we've forgotten?
Jitter.
Well, yeah. Do you want to take that?
I think
Yes. Sorry, I didn't get your hint, Magnus. Yeah. So for my PhD, I worked on modeling Wi-Fi and looking at how the Wi-Fi MAC layer introduces latency. And one of the things that are really fundamental with wireless protocols is that there's this distributed competition to get access to the radio frequency, and that is not a very predictable process. So sometimes you can you are lucky and you sort of win access to the frequency a lot, and then you get to send a lot of data. And TCP, for instance, would sort of see that as, oh, this link is good, I can send lots of data over this link. But then suddenly you're unlucky and you lose that lottery for access to the frequency. And when that happens, the effective rate that you get is suddenly much lower. And then the problem is that TCP or QUIC or whatever other congestion control protocol you're using was aiming for the rate that you got when you were lucky. And if that rate is not the average rate, it's higher than the average rate, and then it drops, then suddenly TCP or QUIC is sending too much data. And then you get lots of queuing. And the amount of queuing that you get just depends on sort of how far is it to the sender, and how many slots are there in the buffer, how much data it can fit. But it's really a fundamental problem, because this randomness of the link introduces a coupling, if you will, or a correlation between the amount of buffering that you add and the actual throughput that you get.
Very cool. Brennan, I heard you had a good latency story. Can you share it?
I don't know if it's a great latency story, but it's one that at least, it was important to me. At the end of the day, latency impacts all of us, and many of us don't understand why. So, when I was in university, there was a bunch of us inside of a home, and we had fantastic internet on paper. We had plenty of bandwidth, plenty of speed, but we were still having an absolutely terrible experience. You can imagine 20 students all trying to compete for the same pipe over Wi-Fi. Things would be tough. And, I alluded to it earlier. This was something that brought me to Ookla. Well, there was an issue with one of the major, I guess you could call, broadband providers within the United States, especially how they had their network set up in the Seattle metro area. There was buffer bloat. Their technology as a backbone was known for it, but there was a misconfiguration specifically in the head end. And this is what got me connected up to our CEO, Doug, many, many years ago. And this is something that, it's what ultimately got me into the telecommunication space. It's what brought me forward here. But most importantly is, this is a story that many people encounter. They just don't really have the tools to fix. So this is something, at least at speed test, we've added loaded latency. We're doing round trip times every 100 hertz, 10 times a second. We're constantly trying to measure that. And we'll be bringing this forward to people, to consumers, to try to bring it forward as a first-class metric, so that people really start calling out their, different providers of like, hey, this is a number that's important to me. That's important to my experience. Because you talked about, I think Bjorn, you brought up consistency, and that's a huge one. I did say gaming, is a common case for it, but there's many patterns in our industry which will try to fudge time. We'll essentially try to guess what's going to happen. We'll simulate it, and if it's wrong, then we have to correct it. If we're able to have a consistent latency, it's a lot easier to do that. You're able to guess, okay, I have roughly 100 milliseconds I need to guess. But when latency is very spiky and jumpy and difficult for those algorithms to predict, it's almost impossible to be able to have a good experience and to be able to handle that heuristic. So I'm hoping that this is something that people really start bringing as the forefront, not just for gaming, but for all these connected experiences we rely on. And I think, Dave, this is something that you've worked on in the past.
Well, I've been pushing folk towards the Nyquist rate for VoIP, which is 10 millisecond sampling rate. When we built CDs, we figured out what the audible range was for the human ear, and we've settled on 44 kilohertz as the correct number for that. And we need to find the right sampling rate to see the details of what's really going on in the internet. And I hope that 100 milliseconds is just a start. But the level of detail you can see if we start going even lower, and the kind of problems that we see will change. So I did want to.
I've heard you talk about kilobits per millisecond instead of megabits per second.
Yeah, 30 kilobits per millisecond, because that's the resolution at which we actually perceive stuff. As a musician, I can perceive. It's widely said in all the standards and the ITUs, stuff like that, humans can't perceive less than 20 milliseconds. Oh, no, it's much lower than that. It's easily well below 4 milliseconds. And we should try, I have a paper on this, we should try to strive towards an internet that has imperceptible latency. And to do that, we have to measure it below perception. I did want to talk to one of my scary things that I've been working on for a while. I have a talk tomorrow about the lower level stuff. May I digress into that?
Of course.
Okay. So when you start looking at the network that way, you have sawtooths for TCP and you have steady packets per millisecond for VoIP and video conferencing. And you can see these two things interact. And I call it riding the sawtooth in one of my other talks. The thing I was so concerned about and remain so concerned about all of our networks today is that the LTE networks and Starlinks of the world and many of our Wi-Fi networks are horrifically overbuffered and running essentially out of design spec. If you have more than about a quarter of a second of latency, bad things start happening. And there's a thing called congestion collapse, which has kept a lot of the theorists awake. And I actually believe is happening every day on many a corporate campus and on many an LTE network today. Only we were looking for it. So you see sawtooths not coming down, and the network just becoming completely useless until people give up and go away. So I would like us also to focus on trying to not have that happen on Mother's Day and
So it's
other workloads.
Higher resolution measuring and also mitigating it, right? And I think like all three of you have alluded to, Brennan, you said, on paper, your network was really good. And I think, Benirad has been working on Wi-Fi a lot where, you get theoretically over a gig and still everyone is having poor video conferences occasionally, right? So Dave, I see you raise your hand.
Oh, you're muted, Dave.
I've worked on Wi-Fi my whole life, and it was the focus of the Make Wi-Fi Fast project, which is now the default in the Linux kernel. And we're very happy to have mitigated latency in that stack, but there's a lot of stacks left to fix. My big thing, and this is partially not necessarily aimed at Ookla, is that a Wi-Fi network is not a point-to-point network. It is a shared network. So somebody over here doing a big download can possibly mess the guy up over here that is doing a voice call. And almost all of our tests just test for those two people connected to each other, not 16 devices in the room all doing different things. And this is one of the nice things about Wi-Fi 7, I hope, in that it will manage multiple devices better. But for the 18 billion existing devices, if you plug them all in at the same time, that gigabit you thought you were going to get can drop to 30 due to things like congestion collapse over the thing there. So those listening, please test your networks under multi-user loads and watch that the bandwidth number drop catastrophically.
Because Brennan, you've been key to bringing latency under load to the forefront of Ookla's metrics, right? And I also saw we got a question from the audience to how will you start using this in your reports? Because I and many others think, if we get this higher level in the organizations within the telecom industry, things will improve more rapidly.
Yeah, absolutely. First off, I'd like to say that we weren't alone in that. There's actually some names I see in the room here who we worked very closely with to bring it to reality. It was not just a Ookla thing by any means or measure. And there's plenty of other tools who also measure it well. Apple has an excellent command line interface to test it. There's other testing providers out there, and that's good. We need it raised up in all different platforms. The question of, okay, how do we start raising its visibility? This is something that I've been working very closely with our marketing team on. The best answer I can give is expect to see more. We want to help drive investment in the last meter. What you're talking about, Dave, how do we help device manufacturers quantify that last meter hop? And that's something we collect to this day. We actually do measure latency from the UE, the user equipment, to the first hop. But then we also want to look at last miles, like how do we help CDNs optimize themselves? How do we help people see the values of CDNs? This is one where there's kind of a misconception in the world that, content delivery network, you're delivering content. But more and more, companies are using these as application delivery networks. But it's a cost, it's an expense. In many cases, we're in a CapEx constrained world. So we cut that expense. And I think it's up to us to really communicate that, no, that last mile latency you just introduced, that has a material cost to your users. And, we're businesses and to your top line, and how do we communicate that forward? So expect to see more from us. We will be reporting on it. We released this feature in May of last year. And we don't like to talk about something until we fully understand it. We have data to back it, and we have actually, we don't want to rush it to the stage. So this is the year where we're going to be breaking the 1 year mark on our data, and we can really start talking about trends. We've also provided it as of last week, not to give a shill, but Ookla, we provide a subset of our data for free, open, gratis. Anyone can download it for research. The UN uses it, the European Commission uses it, and we added loaded latency to that for download and upload. That data originally was used to help push things, and I'm really hoping that researchers start using the loaded latency side to push things as well.
Thank you for that.
Yeah, that's really good.
We'll see.
Thank you.
Yeah.
Yeah. I think the loaded latency is sort of that's in a way it's measuring the worst case performance, right? Not really the worst case, but the sort of tail end of the performance, right? And to the point we made earlier about reliability, reliability is one of those things that is sort of everyone agrees that we should have it, but then what is it and how, like how many nines, right? How many nines of reliability do you want to go to? Is P99 latency the right thing to optimize for, or is it something else? And sort of to give an idea
Steady
of
packets per millisecond.
Yeah, and it's but it's sort of to get an idea of how many nines we really need to be aiming for. It's like a video conferencing session like this. If it's lasting for half an hour and it's something like it's 20 packets a second or something, right? Then that's a lot of packets. And if you get only, you don't need to miss that many of them to notice that something is like lagging or getting stuck or breaking up the conversation. So we really need to be aiming for a lot of nines to have things like video conferencing and VoIP, and especially if you want to do things like musical collaboration across the internet, that it really needs to be very, very good.
How many scratches on a CD do you need before you don't like listening to it?
Yeah, good analogy.
Mm-hmm. Yeah.
Those of you
people don't remember the best
CDs.
experience.
Yep.
I mean, people don't remember the best video call they had, or you talk about even emerging experiences. People aren't going to remember the best experiences they had. They're going to remember the weird, glitchy time that didn't work, that struggled, that you were talking over each other. It just didn't work. People will remember that, and they'll be left with a bad taste in their mouth. And that's super important for these next generation services as well. If they want to get off the ground, they need a strong foundation to be able to rely upon. It's something that's a requirement.
I like the another analogy is sort of if you're building a plane, then it's really important that the metal that you're building it out of is a consistent quality. Because if the metal is sort of a varied quality, then all of the parts have to be slightly bigger, because you need the weakest point to be a certain amount of strong, right? And then your plane gets heavier, and everything needs to be bigger and bulkier and more expensive and less efficient, and you can carry fewer passengers, so everything just falls apart if the metal is bad. And it's the same thing with the internet. If even just one hop along the path has lots of buffer bloat occasionally, then your low latency interactive services are going to suffer sometimes. And then then you need more jitter buffers in your applications, and everything just slowly sinks into a poor user experience.
Yeah. I mean, I think that's one way the industry has approached solving buffer bloat, is throw more bandwidth at it. The higher that you're able to push things faster, you're not hitting, buffering as often. Now, the thing is, we get a lot of questions, in terms of, how do you measure loaded latency? How do you push it? Do you put set rates and measure at, say, 2 megabits, 5 megabits, 10 megabits, or do you max it out? There's different philosophies in the industry on that. My personal one is you max it out, you push it to the nines, and then you measure what latency is, because effectively it's, especially with fixed wireless access coming out, this question has come up with 5G, is, that I've been told many times of, oh, well, there's no real world scenario where you're going to max out 1.2 gigs on a single device over 5G. It's just not ever going to happen. But my counterpoint to that is FWA is one of the best technologies we have to bridge the digital divide to help. Dave, you're on Starlink, and that's fantastic, but it's not necessarily economical for everyone. It's that kind of tier. Like fiber is ideal, no question. FWA is a good economic alternative where fiber is not possible. And then once we're really into a complex scenario, like on a boat, then you do need something like satellite. And it's this nice tiering. It's not one technology versus the other. But with multiple devices on a network, you absolutely can hit 1.2 gigabits a second. Something backing up to the cloud, someone doing content creation, you absolutely can hit those numbers while someone else is on, they're on a very time-sensitive application. So I hope that the industry aligns upon pushing the connection to the maximum, testing out this bandwidth, but we'll see. That's our approach, but we'll see what the industry lands upon.
I'm kind of infamous for taking on Elon Musk and getting him to fix the Starlink network. It is uploads that are the most disturbing from the buffer bloat perspective. And that's, in my mind, impairing future use of the internet. If we make uploads painful for users, then they won't use them and we won't come up with new applications that would. If we can put some focus on both sides of the connection moving forward, we'll see a better internet.
Thanks. And I think I'll give this to Björn. So kind of, why can't you just throw more bandwidth at it? And now I'll give a hint, because he had a bit of latency earlier, and it's often due to that there's a Wi-Fi or mobile link before, right?
Yeah, I mean, more bandwidth is great because that makes it possible to download games quickly and all that kind of stuff. But a video conference only uses like 5 megs, 10 megs maybe, and then what matters is the latency and the reliability. It's what you really want is to be able to have a half an hour or an hour session with no glitches in it, and that's a different kind of thing. Optimizing for bandwidth does not automatically give you that. You have to optimize for bandwidth and reliable low latency at the same time.
And a part of that is because of what you talked about earlier, right? This Wi-Fi link or mobile link that has such high variability, and it's the difference between what TCP and UDP and QUIC expects of the bandwidth, and it's the change in expectation actually that leads to latency, not necessarily the size of the link. Right?
Yeah, totally. And then any jitter or variation on the lower layers is compensated for by jitter buffers and that kind of thing in the application, but that adds latency as well. So it's like you can have some jitter and some unreliability, but the cost of that is more latency at the higher layer. So it doesn't go away. You can't remove it.
Okay, we're running out of time, but
we have a metric ton of questions. Yeah. We have a metric ton of questions from the audience, so go ahead.
I'll just read them out. So from Kevin Smith here, we have a question on, he's been trying user collaboration technologies on cellular network, and for him it seems like jitter is as important as max latency. What technologies do you think can solve both, Dave?
Yeah, so there's been a lot of noise about cloud gaming, and I would like it if the cellular industry as a whole would focus on a first-person shooter like Quake, 1 packet per 20 milliseconds. And if they can make that work, then we can talk about cloud gaming and audio collaboration. The uplink scheduler on LTE is programmable by the operators, and it's usually set to a very high rate, and I would love to see that change. As for more stuff, I don't think I can handle that in the context of all the questions. Let's talk later.
Okay, so one final question from Satish. Just like in the management chain, there's a reverse appraisal. We need such concept as a sender and receiver end. TCP does this with ACK messages, but we do not have this luxury for UDP. some new concept needs to be there so that the algorithm sending rate aligns with receiving capacity. Any comments from the panelists?
Maybe I'm misunderstanding it. Could you repeat it one more time, Magnus?
Okay, so I think that the question goes around how do we understand what quality we're getting, and how do we know for UDP traffic, like most real-time traffic is, yeah. You don't know how at the network protocol level, you don't know what the quality is, right? Because you have no response. And like I can add, like there are technologies like L4S that are looking more into how can you tune a network around this. But any more ideas from you, the panel?
I mean, that's one very fascinating, you talk UDP in the industry now, you instantly go to Quick. That's the really common answer. But one of the amazing things about Quick is that you get to put the congestion control algorithms in user space. You get to manage that in user space. You get to handle that there. And there are starting to emerge new congestion control algorithms at that layer. And my hope is that, we always will need some form of feedback loop. Cutting edge industries, they will be able to develop their own custom quick stacks. They'll be able to handle that. And then for others, they can rely on, CDNs, companies that have R&D teams invested in maximizing performance, into making that also an option. Go ahead, Dave.
I am so delighted to be bringing a new generation into this very thorny problem. Congestion control has been a niche technological field for a long time. To see the uptake and interest, it's really great. I hope you figure it out, kids.
Thanks, you. Björn, I think that was mostly directed at you and Brent.
All right.
Go, kid. Go.
Okay,
Thanks,
so kind of we're at the end here. Do anyone want to do a 30-second summary on what causes latency, which was what this panel was called?
I think the predictable one is speed of light. That's a constant, and you tie that back to distance, get your shortest path, and that's a consistent latency profile we can do, and it's buffering. There's the unexpected side, either at the application layer via packet drops and having to retransmit, or lower layers as we move down the stack.
Yeah,
but
we
we have
missed
to ultimately
retransmit.
solve it.
Perfect, Brent.
But between the absolutely.
Yeah, and then the final thing is jitter that you can't remove, and that needs to be sort of wrapped up into jitter buffers and that kind of thing.
Exactly.
Okay, very cool. We have our next panel starting in 5 minutes. We promised a little break, so I would just like to thank Björn, Dave, and Brennan a lot. It's been great, and we didn't even get to answer all the questions. But if the panelists want to stick around, they can actually type in the answers. So hopefully they will do that. And we'll have a 5-minute break before the next panel is starting, which also has some great panelists.
Good to see you guys.
Thanks for having us.
All right,
And thanks
we'll be back in 5
thanks
minutes.
for putting this event on.
Thanks for joining. So run and grab your coffee now. You have 5 minutes before the next panel starts.
All right, let's get back to it. So for our second panel, we'll be talking about it's titled From Latency to Application Outcomes. And our speakers are Varun Singh, Mayur Sarod, and Magnus Olden. So Varun is the Chief Product and Technology Officer at Daily. And before Daily, he co-founded a company called callstats.io. And so he's an expert on real-time video applications and WebRTC performance. Do you want to introduce yourself? Anything more than that, Varun? We can't hear you. Sorry. Now you're muted in Zoom. Now you're unmuted, but we still can't hear you. Okay, well, you work that out. Mayur has been collaborating with industry and standard organizations to create XR-ready networks for a long time. So Mayur, do you want to introduce yourself? Anything more than that?
Thanks, Bjorn. I hope you can hear me.
Yeah.
Yes, we can hear you.
Okay, perfect. Good morning, everyone, and thanks to everyone to taking out time to join this great panel discussion and the whole latency event, which I've been looking forward for a long time. I'm joining from Vancouver, Canada, and personally, I'm a technologist, and I'm here to collaborate with the computing, cloud, and the network industry so that we can enable spatially computing devices. That's what I'm passionate about. A new wave of thin clients, which I see will change the way we compute. And for that, all the three industries I mentioned have to collaborate closely and definitely need low latency networks.
Cool.
Thank you.
Thanks. Varun, do you want to try your microphone? We still can't hear you. Sorry. All right. So then let me introduce Magnus Olden, the moderator of the last panel, CTO of a latency management company. So he's titled himself here. And Magnus, anything else you want to add?
No, I mean, we do latency management, so hopefully we know a bit what we're talking about. I have also with Björn and some others worked on what is called the quality of outcome framework, which has been sent to the ITF, is now an internet draft, but it's essentially how do we go from dirty, difficult to understand network latency statistics to application outcomes. So again, hopefully I do know something about the topic of this panel.
Great. Thanks. Now you're muted in Zoom, Varun.
Let's try one more time.
Yeah, there you are. Very good.
Perfect.
All right. Anything
Yeah,
you want to
today-
add?
No, I don't want to add. Like, I guess this shows how complicated sometimes simple systems can be.
Yeah. All right.
Let's get started.
Cool. So let's just jump right into it. So why should consumers and service providers care about latency? Start with the hard one.
I guess I can start because I had so many issues right now. Just to say, like, quality of experience is like the most important thing for like end users, right? Like we talked about gaming in like 5 seconds ago, and we're on video conferencing right now. So quality of experience of each of these applications is why end users care about. And the underlying thing is always about quality versus timeliness. Timeliness is like a function of latency typically. So if you want to have really good timeliness, you want lower latency. And if you want higher quality, and you can trade off some of the timeliness in some other factors, you can increase latency.
When you say
and get better quality.
When you say quality, you mean resolution, right?
Oh, well, that's a really good one. Quality of experience can be measured by many things. Like it can be latency as one of the aspects of quality. Typically, the way I think about it is like you would have resolution and frame rate on one side and timeliness of playback on the other, right? And then the question is interactivity. Like if you want really low, high interactivity, low latency, then you can't have typically the highest quality that you want. You're trading off that with some kind of latency. So I think Dave talked about like perceptible at 5 milliseconds or 10 milliseconds earlier for music. Then you can't actually send like 8K resolution unless you are in close proximity, have really good infrastructure to support that. If you want to do it over the internet, you have to like kind of figure out the trade-off of quality of frame resolutions and frame rates to like interactivity, and then come down to timeliness.
Yeah, I think like fundamentally, users go on the internet to consume applications, right? Not speed test results or bandwidth. That is why we're here, right? We want to use application, and we want to use them to collaborate and be interactive. So that's kind of the absolute fundament of what any network operator should care about. It's the outcomes of the applications, right? Is the video conferencing, how high a resolution is it? What is the timeliness? How interactive can you be? How big is the chance that Major and I will start talking over each other at the next silence? That's really what we want to reduce, right? And really, latency is such a key part of that, right? And it's been like the theme all through this today, right? Starting from Gavin, but also the previous panelists, that you just fundamentally cannot just look at bandwidth and say, hey, we fixed the bandwidth. No, it doesn't work like that, because latency, how latency distributed, packet loss, and lots of other details really do matter for the outcomes of applications. So that is why network operators and anyone really in the industry should care about latency, because it translates. So it's such a key element for application outcome.
Thanks, Magnus. And I would just like to zoom in into the applications, right? Today, we see there are a lot of real-time streaming applications which work fundamentally different than how we used to access OTT kind of data, which was more burst kind of streaming. With the real-time streaming with the video conferencing, gaming, AR, VR, right? The data pattern is more isochronous. So it's a bit more technical, but what it means is that the latency is very critical, because now we are on a video conference. The data needs to reach in fixed intervals, right? It cannot afford to buffer for a long time. So for me, I'm very excited about spatial computing. So so as we see a lot of AR VR devices which are quite bulky, and it's for a reason, because most of the compute is happening on board. But as network technologies get mature, as operators start to see the value of low latency, start developing low latency in the networks, that compute will be offloaded to a cloud. And then we start to see really thin devices which will change the way we compute. That's what I'm really excited about, and hope that will like bring new applications for consumers.
I guess a key point here is also that we are, both Mayur and I worked a lot in standards industries, right? And what we see is that, I would say, for the first time, that the application vendors like the Metas who have their Horizon and Microsoft, the HoloLens, these are really starting to get involved in the standards bodies, just because they see that we fundamentally need lower latency to be able to get AR and VR to happen at a large scale, right? And then you alluded to this also earlier, that we can't have a GPU that runs hundreds of watts, running in our headset, because for many reasons, right? So we need to offload that in some way. So kind of the future is even more, say, latency sensitive.
Correct. Yeah, and the requirements for latency is very tight for AR, VR, especially the head poses that has to be sent periodically. So definitely any kind of jitter or any kind of contention in the medium will cause degradation in user performance.
What kind of latency budgets are we talking about for an AR, VR application?
So, good question, Bjorn. So we have to come back to how we perceive images, right? So there's something called VOR, vestibular ocular reflex, which is basically a way our eyes correct for very fast movements of our head. So when you are wearing an AR, VR devices and you are moving your head very fast, our eyes move in the other direction to correct for the image that is created on a retina. And for that, you need a latency of 7 milliseconds. That's the time the eye needs to stabilize the image on the retina. So now you imagine a user doing a gaming session on AR, VR, and he's moving his head very fast, right? So the head poses have to be sent back to a cloud system and be back to the HMD within best case 7 milliseconds. So it's an ideal case for the best kind of performance, but usually I think 20 millisecond round trip time is accepted for a good user experience.
And Varun, how does that compare to the requirements of a video conferencing application, like something WebRTC based?
I think end-to-end latency is about 100 milliseconds, 150 milliseconds are quite okay. We're talking about videos that are being generated at 15, 30 frames per second. So that anyway being generated at 30, 60 milliseconds intervals. So typically, like for an okay experience, like right now with so many participants, I think we could even have like 200 milliseconds, 300 milliseconds latency, then it's acceptable. Because humans can perceive, like while they can perceive latency, they can also like make the compromise. Absent this, like they can't have this conversation at all. So, and if you remember like from like 15, 20 years ago when you had satellite telephony and you would have like really larger latencies in satellite telephony, it was more like walkie-talkie. But as soon as you figured out, it's high latency, you would like talk, pause, the other person would speak. It's not ideal, but it's still something that humans can cope with. What I think most people hate is when the expectations get broken. So if you were on satellite, like let's say satellite link, but they didn't understand of satellite link, so low latency, then high latency, then low latency, some people call this jitter, variation of delay. That breaks like humans' expectation. Like we just understood that, it was high latency, I know how to behave in this. And suddenly that contract gets broken, then it creates like a bunch of chaos and people are super annoyed by that.
So reliability is more important than the absolute latency numbers for something like video conferencing, but the user experience gets better as low, like if you can lower the latency, the user experience improves as well.
Yeah, I think it's a tough decision between reliability. I think what I would say is target a latency and like set and don't vary that, right? So like basically once you target something, you set it up, then don't go lower or higher with time. Because like if I talk to my grandma and she understands that, this is going to be slow or high latency, she can actually cope with it. But like 1 second it is short and 1 second longer, then she just gives up and says like technology sucks. And that's frustrating for people.
Yeah. Right. So I guess to all of you, what would you say, to what degree does the networks that you've been working with or the applications that you've been working with deliver on that?
Well, they deliver, but not reliably, right? I think back to the same key question. It's like, how can we, video conferencing works most of the time, but it is really annoying when it doesn't work. And especially, when you get to like cross-Atlantic video conferencing, like we're having now, right? Kind of, we have some physical limits to how good it can get. but then anything on top of that just adds to the frustration. And back to Varun's, what he was saying, if we're halfway across the globe from each other, well, that's 70 milliseconds ish getting there, but it's that variation on top that really makes it difficult. And I think like all of us are having, a lot of us are in a lot of video conferencing calls these days, and I don't think I ever met anyone who said like, oh, that's never a problem.
I
But on the
agree.
flip side, I think,
Yeah.
just to interject a little bit, like I think WebRTC has done such a great job of like setting good expectations on quality and experience. I think I would say like 99% of the time the experience is better than it was like 10 years ago when we didn't have like the standard or like the working conditions to make it work.
I agree with both of you, Varun and Magnus, right? I think the problem with reliability is when do you measure it? Because if you do a measurement of quality of application outcome, right? When an unloaded network, it might work very well, or in a lab, it might work very well. But the variability that is added because of what Bjorn mentioned before, the way Wi-Fi medium is accessed, and in this, it's a base competition based, that creates a variability, and that is in question on reliability of a session, right? And I think that's the key. Like when I go into an important call like this, I want to be 99.9% sure that I have a good link. I will not have a video drop, right? And it's very difficult to get that confidence on a Wi-Fi link, right? Because it's competition based. So that's something which, we need metrics to understand if links are getting worse, and quick mitigation actions to fix it.
You're speaking very close to my heart now, Mayur, because this is kind of what we've been working on for a long time. This way, you're speaking to the challenge of essentially how do we measure and monitor networks, and in a way that means we can make sense about how the application outcome will be, right? Because this is this challenge you're talking about. You're saying, and I feel the same way. You go on a network, and your network, and you're just not sure. If it's important video call, right? Is it good enough? How do I know? Right? And it's really challenging to measure that, both as an end user, but also like I work with network operators, for them to understand and monitoring this continuously. Like Dave and Darren and Brennan mentioned earlier, it's typically when things get very loaded that the problem occurs, right? And that is, maybe 1% of the time, or maybe it's 0.1% of the time, right? But if even in this webinar, it sucks if my networks just drops 1% of the time, which means if it's 20 packets per second, then that's every 5 seconds I will have some packet drops, and you may have struggled to hear what I'm thinking, right? So kind of this is what we've been able to have a talk about it on Wednesday, but this quality of outcome framework that we've been working on is just to be able to do this, right? To better go from looking at network statistics and latency distributions to translate that into, hey, on this network, you actually have 100% chance of perfect video conference, or maybe not 100, but 99.9, right? On this network, you have an 80% chance, right? So that both network operators, but also applications and end user can understand something meaningful about what kind of application outcome can I get on this network.
That's a good point. That makes me think of sort of there's not much communication between the layers here, right? The application will know if it's working well or not, but the ISP is just delivering a service, or the ISPs along the path is just delivering a service, and they're not notified or in any way informed that something is wrong at the application layer. And what do you think about sort of that coupling, or is there something doing something like that today, or is that something that's missing completely?
Personally, I think now it is missing, right? Byron has been part of building WebRTC, which is a lot of time. How do we fix a unreliable, or how do we make the best out of an unreliable network, right? And because from a WebRTC point of view, you just have to live with the network. There's nothing you can do about it. On the other side, the network equipment typically don't really have any real-time insight to what kind of applications are being used. What are they being used for? Do they have network requirements? I mean, there are QoS or ESCP bits and whatnot, but they're usually not set, and typically the network does not use it in this way. So there is a huge gap between there, right? And that's kind of how the internet was designed. It's design choice. But now we're seeing stuff like a Kamara project where you're starting to see, can we expose APIs between the application layer and the network layer, so we can have better understanding of each other. Because now we're working in our separate areas and separate ways.
Right. I mean, to fix this problem, right, it is not a single layer problem. So I believe in making a strong foundation for a house, for taking an analogy of the house, right? Fixing things in the PHY layer I will start from L1, antenna diversity, getting Wi-Fi 7 or Wi-Fi 6E for less contention, MLO kind of features, right? Then going up to the MAC layer, the network layer, using new protocols like C2TCP or PRB, L3 and above, right? So I think going bottom up and fixing problems at each layer, and also giving metrics back from the Wi-Fi drivers to the network layer to improve congestion control. Those are the key mitigation steps. But it needs to be done like a doctor, where you do a diagnosis and then you try to fix the root cause based on the severity of your problem.
Since I was called out for, I think the typical thing for WebRTC, and I think, is that if there is any help from the network, that's helpful. But typically, the assumption is the network should not queue, if anything. Right? If it doesn't queue, we're all okay. And I think it's also a philosophical question, like if there would be gaming applications which get better, let's say, experience because the network understands this is a gaming application, then almost everything would say that it's a gaming application, right? So if there's a fast lane and there's a way to get into the fast lane, then why wouldn't everyone fudge to get into the fast lane? So, and I think we can have a long discussion on it, and there are both sides which have economic reasons to like think about it in slightly different ways. But eventually, like this all has to come together, and endpoints typically make decisions independently of like what the network. It can take hints from the network, and if the network is fair and provide some unbiased input, I think it works both ways. I think both of them can collaborate. But it is also possible both can cheat. So
That is true.
Yeah.
And I think like you had a point, like it's WebRTC kind of wants everything to be non-buffered, and I know Dave also wants that, right? There are no queues in a sense. That would be perfect for WebRTC. So from network operators' perspective, that is very challenging, because if you have no buffering, that means speed test result will be lower if you have a shared connection, right? So you there is an inherent trade-off that is happening all the time, where people are adding buffers for better speed test results, or not just speed test result, but better bandwidth utilization, maximization of bandwidth. So that trade-off is there constantly. And I know like Matt is he was Googled for, and he was part of our last webinar, and he actually said, if end users understood how important latency was for their application, compared to the bandwidth. Once you get to a certain point, we would have fixed the latency problem a long time ago, right? The problem, or one of the problem, is that we're not selling networks as how well will video conferencing perform on this network. We're selling it as it has 100 megabits per second up and 100 megabits per second down, right? So it really is, if we can go and say educate users that actually latency matters, but what matters the most is the application outcome. We can come to better standards, better ways of working with application outcomes instead of, say, network statistics, and put that forward to end users and applications and network operators. I think we will have a much faster path to low latency network, right? Because fundamentally, it's challenging for a network operator to trade off bandwidth in any case, right?
Yeah, this is somewhere where, oh, sorry, Mayur, please.
Yeah, just wanted to add, like, from the AR, VR perspective, right? Like, if we look at split rendering, the bottleneck is the head post data, which are very small packets, which have to be sent up very quickly from your HMD to a cloud renderer, right, and back. So I think also what we have seen is a lot of queuing happens in the uplink direction, right? And so Varun talked about the fast lane, which I think is required, especially how to do that, how to categorize it is a big, of course, a question which can be debated, but it's not necessarily for video packets, but for small payload packets, right, which needs to arrive very quickly and be sent back quickly. So I think that's where we need to have some way to provide a priority to this data with DSCP marking or other methods.
Yeah, it's possible that that kind of delay budget is something that's not compatible with the best effort approach. Is that what you're saying?
Yes, yeah. Exactly.
Yeah, so what Magnus said earlier made me think that this surfacing of how important latency is something where, or it's something that the applications can help do, right? If applications were, and speed tests like Ookla as well, if they surface latency metrics more prominently, or even just notify consumers when the latency is too unreliable or too high, then that might create the incentives for ISPs and vendors and everyone else to focus more on the problem, because it's not like the solutions aren't sort of invented yet. It's more that they are not deployed, right?
That's a good point, right? Because you see, I mean, I'll ask Dave directly, but how long is since FQ code was released, right? It must be 10 years almost, right? And the kind of
it was released in May of 2012.
Okay, 21 years almost. So kind of solutions are there, right? But they're very rarely implemented. Or it's getting better, but it's taking this much time to get. It's an open source solution, it's there for free. Why isn't it everywhere, right? And I know there are challenging putting that into network equipment and hardware acceleration and blah 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 blah. There it's not always super straightforward, but if end users and network operators had started caring about latency a few years ago, then I'm very sure that we would have seen a lot more deployments of these solutions, right?
Yeah. So we have a couple of questions. Neil is asking, or Neil Davis is asking, I feel the endpoints are entirely capable of figuring out what they need to do. Perhaps if the network did not queue data very long, the applications would figure out what needs to be done. And is asking, can we exploit control theory here? It has a lot to say about how tight in time the feedback has to be to get control within a particular accuracy. I guess that's about feedback from the network, or even sort of passive signaling from the network, in a sense. Any thoughts on that?
Yeah, kind of. I also think that if we had, say, no buffering, right, then applications would have figured it out. Problem is now we have buffering, and you just need one link that buffers to make it a problem. And if we are in a world, which we are, where you know, like our video conf or our webinar here is not just spanning one ISP, right? There's going to be like probably 5, 6, 7 network operators along this way, right? And if there were no queuing, we would have figured it out, but queuing is there. And if just one link starts to queue, we have a problem. So the problem with this sort of approach is that you need everyone to switch at the same time. So in theory, yes, I think it's challenging in practice for now, but I also think it's the future we should aim for.
Cool. And then the final question is, do you know of any attempts to measure the throughput given a bound on latency, is how I'm interpreting that question. Has there ever been an attempt to measure speed of packets under a certain latency only? So if you limit the latency, what's the throughput? What's the bandwidth? Do you know of that kind of attempt?
I mean, delay-based congestion controls are a thing, and I think WebRTC tries to do that as much as possible. It does try to tune the latency a little bit. It has the jitter buffers, and like the buffers can increase at the endpoints from like 10 milliseconds all the way to 200, 300 milliseconds. So that system in itself tries to regulate that aspect. So the sender and the receiver try to coordinate as much as possible to kind of optimize for a throughput within the delay budget.
Right.
Thanks, Varun. So from practical experience, right, like if you do throughput test on TCP or UDP, right? So on TCP, what happens is if you have latency on your link, your max throughput will come down, like because TCP max tries to push as much as possible. In UDP, you will start to see packet drops. So you will see error rates. So I think that can be an indication of the impact of latency on throughput, right? So on UDP, you do have fixed throughput, but then you see very high packet error rate. But on TCP, you will start seeing lower throughput when latency is getting larger on your network.
Yeah. All right. So that concludes our panel. Thank you very much to all of the panelists. And our next speaker is Varun. So please just stick around. And feel free to start sharing your screen whenever you're ready.
Thanks for having me, Bjorn.
Thank you.
Great.
Thank you, Bjorn. Thank you, Magnus.
Thank you. Let me switch share screen. Or just do this one. You all can see it?
Yes, it's looking good.
All right, so I'm gonna, it's a fast follow to what we just talked about. And this is just my thoughts over the last 10 years working in this field. And it may feel a lot of like basics being covered, but I just wanted to get it out so people have a vocabulary, and it's just a starting point of conversation for us. So I've started all my presentations over the last 10 years with this Geek and Poke comic strip, which kind of explains why latency is so important and interactivity as a consequence of that latency. And a lot of the conversations that we have with our customers, with the end users in video conferencing, is about the trade-off between quality and interactivity. And sometimes that conversation is tightly on network jargon, which is bandwidth versus latency. And we know that if we want more like we can have a lot of bandwidth available today. And a lot of the times the end users end up saying that I'm paying for 100 megabits per second, or 50 megabits per second, or 1 gigabit per second. And the video call is only doing like less than 10 megabits per second. Why can't I actually get the 10 megabits per second? Of course, like there's a lot of things to unpack in this conversation, because like, where did you measure the latency to? Where did you measure the bandwidth to? When you're having a conversation over video, where is the end person? What is the constraint on your network or on the other person's network? And through COVID and the pandemic, we've seen like these calls are not just one-to-one. They're typically large group calls, can be 5-7 people on average, but can easily be 100 people like right now. Like there are like 5 speakers, but hundreds of people listening. And the experience needs to be managed vis-a-vis, across all these things. And there are a bunch of things that we'll talk to, like in terms of what we can do to do that. So I reframed this question about bandwidth versus latency into quality and interactivity. And depending on what type of application you're building for video, you could have the highest quality, and you may have to trade off some interactivity. So if you want to like consume raw video, no one's saying that you should, and don't want to, but if you want to get 4K video, and that's a lot of things that happen in ingress sports events, is straight camera feeds go right into a sports center where they're compressed and then distributed. You want the highest quality. There is interactivity delays of like a couple of seconds or 5 to 10 seconds, depending on what type of technology you end up using. So is it HLS, Dash, a lot of acronyms there. But if they're HTTP-based streamings, you can have as low as 1 second, but as high as 20 seconds delay. So from where from capture to the screen on your television, it can be 1 through 20 seconds, depending on what's happening and who you're using and what type of technologies that you use. So if you're doing something like streaming, you can really like say, I want as much quality, and I'm giving up some of the timeliness or interactivity, but I'm also creating this buffer. So what we're seeing here is that it's playing back. You have a buffer that's growing, and you're also reading from the future, so you're getting a lot of packets, and you're trying to administer as good quality as possible in this case. On the flip side, if you're kind of doing real-time calls, you want to have interactivity. Going back to Dave's example of, sub 10 millisecond delay on like a music app, what you really need there is like, very low buffering, packets coming almost in real time. They're very tiny packets. They come through, and you play them back, within tens of milliseconds, hopefully in sub 10 milliseconds. And this kind of, if you think about like what type of application you're building, the application developers are thinking about this all the time. They're thinking about like, what am I trading off? Who am I trading it off for? So in this case, when we have a large webinar, I'm sure like, there is a spread of latency distribution across the 100 viewers that are watching it. And we're using Zoom, so it's kind of like real-time technologies, kind of based on WebRTC or similar, still using RTP and things, different codecs, H.264, for example, in the case of Zoom. It's trying to keep the end-to-end delay across all the sessions around like 500 milliseconds. Some people are getting at 100 milliseconds, and some people are getting it at 400, 500 milliseconds. The biggest test for us in this case would be if someone would suddenly like raise hands, start ask questions. The question is, what information did they have when they asked the question? So are they 100 milliseconds behind reality, or 500 or 1 second behind? So that's the actual thing about timeliness and quality in this case. But we don't build our systems for the best experience. We're actually building in many cases for the worst or bad experience. And there are trade-offs as a consequence of that. And there's a bunch of things that degrade quality even once you made the trade-off. You're saying like, I want low latency. I'm willing to like trade off the highest quality for some optimal quality. What is that? And then what we run into things are variable network performance, software errors, user and equipment faults. Like one of the things that happened right at the beginning of the call for me was like my headset and Zoom did not like kind of play well together, and we had to like kind of give my spot to someone else, get my things fixed, and then come back in. And this is after I had already tested for this at the beginning. So some things can fail during a call as well. So what does it end up being? Some of this is network. Some of it is the encoders and the decoders. Some of it is local device issues. So there's a gamut of issues when you have an application which is as complex as a video conferencing system. And we've talked about in the previous panel and the first keynote, like the trade-offs are typically media quality, network, device. Devices are CPU, battery, how much can you offload to your hardware, how much is it done in software, what is the kind of battery life you have. Like if you have low battery, 20%, 30% battery life, are you making a different trade-off than when you had 100% and you connected to power? The same thing for network. Like, am I on a Wi-Fi network where the link is asymmetric, very high uplink losses, depending on where I'm situated? Am I sitting close to the access point, sitting far away from the access point? Am I moving? Am I pacing? Am I walking out of the door? Then there are things like jitter, throughput that come as a consequence of those behaviors. And then there's media quality, which is what we try to, like when we talk about quality of experience, we're all talking about like an optimal experience with optimal quality, with optimal latency and optimal buffering in this case. And if you talk to an end user, they always want the highest media quality and the lowest of the device and network resources, right? They don't want more of their battery to be consumed. If they can have lower network usage, that's great. But they want to have like the highest media quality. And just like I was talking about 100 people on this call, we like that triangle has different like modes of operation. Some people who are on mobile right now, they have a very short range of operation. They're trading off battery to network and trying to get media quality at a certain level. I'm on a tethered connection with on a desktop, so and connected to power. So I have like the largest like kind of footprint on the optimization that my endpoint can do. And if you think about like these calls which happen like across geographies with multiple people, what the endpoints are trying to do is like figure out what is the common minimum or common optimal, so that they can deliver to those people. If there are people on high networks, there are people on low networks, maybe I can send on my side, I can send two qualities so that the network or the infrastructure can like broadcast to people on low network capabilities the appropriate quality, while those who are on high network capability a different quality. So several optimizations exist as a consequence. You have protocols, you have infrastructure, you have endpoints, and these things need to come together. Sometimes these things are fully controlled. So if you're like a Zoom, you control the protocols, you control the infrastructure, you control the endpoints as much as possible. And then you have things like video conferencing systems, which are fully bespoke. They have room equipment, which the endpoints are controlled by someone else, like so Polycom or similar. Infrastructure, maybe like you have VPNs, you have like corporate networks, you have like ISPs, and all of them have an interplay in those cases. And then the protocol, you have SIP, you have RTP, you might be translating from one to the other so that you have like broader coverage. So typically in terms of protocols, we have like UDP, we have RDC suite of protocols. With Quick, we now start to have web transport, so you can use either or both. HTTP has HLS-RTMP. In some bespoke cases, you could be mixing the both of them. You could have like 5 people, 10 people, like let's say on a Twitch call on WebRTC, you have 2 people on stage, they're having a conversation, podcast style, and then hundreds or millions of people watching it almost in real time, live, depending on, they're using some WebRTC suite of protocols, web transport, HLS-, and you could get to like 1 million people watching it in real time with different latency budgets. One part of the conversation that I find very interesting with infrastructure is typically like the last mile connectivity. A lot of us, like when we deliver high quality video and audio services, we run into a lot of the problems are last mile. Thanks to COVID and the pandemic, with people moving into like their homes, the ISPs actually did a good job of like responding to those needs. And the home networks, at least in the last couple of years, have improved like dramatically compared to like what they had like what a lot of the end users had at home, either because they bought better networks or better plans, or in general, like the servicing of the home networks became better. As you talk about like delivering this, we want to be as close to the edge, as close to the end users. This can be on AWS, can be the edge, or you could have like other pieces of technologies which bring the edge closer to you, like peering with the CDN peering with the ISP, for example. And things like transcoding and simulcast can also be done. Simulcast is like simultaneously broadcasting low and medium quality from and high quality from the end user. So right now it is quite possible that I'm transmitting 3 video qualities at 720p, 360p, and 180p right from the end, like from my endpoint. And Zoom is basically just broadcasting the appropriate quality to you at the endpoints. Or you could do this in the cloud with transcoding, with some variation in delay, with some like expectations in latency. And the endpoint itself, like the media engines and the endpoints are becoming more robust, thanks to things like TikTok, Snapchat. The media engines on mobiles are like as performant as like the old room conferencing systems. Things like error resilience, like FAC, RDX, ULP, all those things are also available. And the OS memory threat footprint, as the endpoints become more powerful and are broadly available, endpoints are able to actually do a lot of these things without the coordination, best efforts from the networks. But the best solutions, of course, like want to make trade-offs across all three features, so the endpoint, infrastructure, and the network, as much as possible. So those were my thoughts, 16 slides on real-time and quality. I'm happy to take questions at this point.
Thank you, Varun. That's a really excellent talk. We do have a couple questions. First one is very long, so I'm wondering maybe you can do that in text. And the other one is, how is RFC 8837, which is DSCP categories, used for WebRTC today? For what traffic, or for which traffic differentiation? Is there any ongoing work to make it compatible with IETF non-queue building low latency traffic?
I think I don't remember if the 88 RFC was for WebRTC, but like when WebRTC started, there was like a strong expectation of DSCP code points. And I think most browsers mark AF42 through 44, the media traffic and the video traffic. And if you're doing PSTN, it might mark the audio as CB. But that's as far as it goes. The browsers, because they implement the media stack, actually make that decision on behalf of the application. The application has a very simple API where it can set priority for audio video as low, medium, high. Like for example, when I was screen sharing, there's lesser, like you can say that my video, my screen share could have like better profile than my video camera audio and my audio. So you could set different priorities within like what I'm sending, and then the browser would pick. I think they came up with the DSCP code points by looking at what could traverse the end-to-end internet from one ISP to the other, assuming that they don't get like whitewashed and such. So I think like the case of WebRTC, it's really what can traverse the subset of DSCP code points that can traverse end-to-end between ISP boundaries is like the main question.
Right. Okay, cool. Good answer. I don't think we have any more questions. So with that, thank you very much, Varun.
Thank you. Good one.
And we'll move on to the final talk of the day. And that is Stuart Cheshire from Apple talking about RPM, or round trips per minute. And as Apple's distinguished engineer for networking, Stuart has been fighting latency both in end systems and in the network itself for many years. He's the creator of Bonjour, which is Apple's service discovery protocol, the author of Bulo, one of the earliest internet multiplayer games, and author of the famous blog It's the Latency Stupid. So please, Stuart, the stage is yours. You are still muted in Zoom.
Thank you. Yes, I was just looking for my mute
Now
button.
I can hear you.
Great. Let me share my screen. Is that the right one? Yeah. So is that coming through now?
Yes, it is.
Great. So I'm our last speaker today, and I'm here to talk about measuring and understanding latency and how we report that to users. We've all seen these comments on social media about people complaining about their network. These are not actual Twitter posts. The real Twitter posts contain language that I wouldn't like to put in a presentation. These are slightly sanitized, but these express the sentiment of the unhappiness that people have. And we're talking today about latency. Why do we care? A lot of times we hear people talk about video games and video conferencing and virtual reality. And I think that's misguided because it leads decision makers at companies to say, oh, that doesn't matter, that's a niche. I don't play video games, I don't care. And the problem is that latency affects everything. And every time we look for driving directions or stock quotes or weather forecasts, we're all used to seeing these stupid spinny wheels saying, please wait. And that's an implicit recognition by all the application writers that the network is too slow. They might not think about it like that. They might just assume that that's the way it is and that's the way it has to be. And it infuriates me the amount of human time and graphic designers' effort that goes into making these visually appealing please wait indicators with animations to entertain the user while the app waits for the slow network. And we all know why this is. I'm sure everybody in this webinar today knows all about buffer bloat. Very quick recap, because we've covered this well. It comes because of FIFO queues that are oversized. Having the queue being too big causes excessive unnecessary delay. And then when the queue fills up, packets are lost, and that requires retransmission, effectively doubling the delay. I have a link here to one of our Apple Developer Conference presentations where we talk about this. This is just a quick excerpt from that presentation of a packet trace I did 8 years ago, back in 2015, where we looked at a packet trace of a data transfer. This was streaming video over a 10 megabit link. And for those who are not familiar, I'll give a quick explanation of how TCP trace works. These little black marks are the packets. We have time on the horizontal axis and the cumulative amount of data transferred on the vertical axis. And you can see to start with, there's a steady stream of black packets, and the purple line is the acknowledgements coming back. And the first thing we notice is that the round trip time between packet and its ACK is increasing. And that's because the buffer's filling up. And then eventually, because buffer's not infinite, the buffer has to overflow. And then we get massive packet loss and retransmission. And it's absolute carnage. But the interesting thing here is if we ignore all of that and just superimpose a straight line on this graph, the graph ends up exactly where it would have been at 10 megabits per second if there wasn't a single packet loss. And that's why measuring network performance, simply measuring throughput with tools like iPerf, is extremely misleading. Because if you ran iPerf on this, it would tell you, yes, you're getting perfect 10 megabits per second. And the reason there is because even though packets are lost, TCP does a really excellent job of retransmitting only the packets that need to be retransmitted, retransmitting them immediately that the loss is detected. On the bottleneck link, no packet is sent twice because that's a waste of bandwidth. And there are no idle times when the link goes idle because that's a waste of bandwidth. So we end up with TCP perfectly recovering in terms of throughput. But if you care about the actual delivery time of each of these packets, it's a complete mess. So the solution to this is smarter queuing in the network. Instead of just having a queue and letting it fill up and losing packets when it's full, we manage the queue. So the bottleneck network device detects when a queue is starting to form, and it doesn't wait until it gets so bad. As soon as it detects a queue is forming, it tells the sender to slow down. And it does that not by dropping a packet, but by sending an explicit congestion notification. I mentioned a term there that is really important, bottleneck queue. A packet through the internet might go 10, 20, 30 hops. And they might all have buffer bloat, but there's only one that matters, the bottleneck. The slowest link is where the queue builds up. And if we fix that link, we have fixed the problem for that user. And that's really important because this is not an intractable problem where we have to fix the whole internet. And in this test I did, when we fixed the one bottleneck queue, this is what the graph looks like. And you don't need to be a networking expert to look at that and immediately see that that is so much better than the previous plot. The black stream of packets never pulls away from the acknowledgement line. Every time the slightest queue builds up, the gateway sends an ECN marking, the sender lowers its rate. The little CWR marks on this plot are congestion window reduced. That's the acknowledgement from the sender that it got the message and it's reduced its rate. And those little CWR hints happen occasionally. It keeps the queue short. There is not a single packet loss. And this is building on the work of Jim Geddes and Dave Tatt. This is using CODL in this test. Fantastic. This is back in 2015, 8 years ago. So we solved the problem, right? We optimistically thought we would deploy these algorithms, tell people about them, and it would all be fixed. And it hasn't. So that caused us to do a little bit of soul searching and think about what did we do wrong. One thing that happened is that there have been a bunch of attractive but wrong ideas in the industry. Because people make analogies between networks and day-to-day human life, they come to conclusions that things that work in day-to-day life would work in the network. And unfortunately, that's not right, because that analogy between standing in line at the airport check-in and packets in a queue is not a good analogy. Packets are easily created, duplicated, destroyed. They can be generated at an effectively infinite rate. It is not like people going to the airport. And a lot of the popular solutions are based on that false analogy. So we think about quality of service or priorities, because that's what we do in day-to-day life. If we want to pay more for FedEx overnight service, we pay more and it gets faster. And all of these assumptions are based on a belief that there's a fundamental scarcity. And in the days of dial-up modems, that was true. But in the days of broadband service today, for most users, that's not true, and yet they still have a problem. Part of the problem is that bandwidth is a zero-sum game. If there isn't enough bandwidth for all of us, then somebody needs to make a decision. The network operator, some network hardware, needs to start making value judgments that my video conference is more important than your video streaming or whatever it might be. But that's not always true. If I'm at home working on this presentation, then my file transfers are more important than my kids watching Netflix. So the question of who decides what's important and what isn't has turned out for the last 2-3 decades to be an intractable problem. The good news is we don't have to solve that problem because we no longer have a shortage of bandwidth. Bandwidth scarcity is not the problem. The problem is how we manage the queue. The problem is not the quantity of network we have available, it's the quality. And the good news is we know how to give low delay for all flows. And that really simplifies this, because when every flow has low delay, we don't have to decide what's more important, what special privileged applications get the good treatment, because they all get good treatment. And this has been a hard message to get across, and it's one we have to repeat over and over again, because people have to hear it 3 or 4 times before it sinks in. It's so counterintuitive, people can't believe it's that simple. Now, this is not just theoretical. We've made progress over the years, and from the Apple side, we now have L4S congestion control shipping in customer builds of macOS Ventura. And you can try this for yourself using a modified version of iPerf 3. And there's network hardware starting to ship that supports this. Low latency DOCSIS includes L4S queue management and other cable modem specific technologies that reduce delay. So this is available now. And if you're running a Mac, you can try it out for yourself. And if you've got one of the newer cable modems, you can see the benefits. So from a technology standpoint, this is all looking very positive. But for years and years, it wasn't deployed, and it still is not widely deployed. And a few years ago at Apple, we were doing a bit of soul searching and trying to work out what we did wrong. We gave this great presentation in 2015 at the Apple Developer Conference, and nothing happened. And then the COVID pandemic came around, and we're all working at home, and video conferencing wasn't very good. And lots of people, I'd say 80% of the people I know upgraded their internet service because they thought that would fix it. And we've gone from 50 to hundreds to gigabit and even beyond gigabit per second to the home. And it still doesn't solve the problem. And 5 megabits per second is plenty for this video conference we're doing now. So how can it be that a 5 megabit stream doesn't work on a 100 megabit network? And the problem is not lack of bandwidth. And until we start focusing on consistent low latency, we will never solve that problem. So we started thinking, what were we doing wrong? And I was reminded of a book that I read in college 30 years ago, Crossing the Chasm by Geoffrey Moore. Many of you are probably familiar with this. If you're not, it's an excellent read. In the 90s, this was the Bible in Silicon Valley for .com startup companies. Why is it that some companies succeed and some companies fail? And Geoffrey Moore identified this market growth cycle. You start with the new technology and the innovators get excited. And then when it's proven, the early adopters get on board, and then it stops. And Crossing the Chasm, the title of his book, was about how you make that leap from the early adopters to the early majority and then the late majority. So then in 2022, we started focusing our minds on how do we get network latency technologies to cross this chasm? And we realized one enormous oversight, which is we need measurement tools. All the measurement tools back in 2022 would tell you your throughput. You go to an internet speed test, it tells you your throughput. And it's not surprising that all the customers believed that was the only number that mattered. And it's not just the customers, it's the engineers working at the companies that make home gateways and cable modems and Wi-Fi access points. And it's their management, it's the VPs making the decisions. They judge their employees on how many megabits the product gets because that's what the customers judge the product on. And we were stuck in this. And what we realized was we shouldn't have just focused on solving the problem. We should have been focused on the education. And that's why in iOS 15, we introduced what we call the responsiveness test. And it's a focus a lot less on throughput, but on latency. And you can enable this on your iPhone. You'll see this responsiveness section. You click on the test button. It will give you a warning. It'll give you a little spinning indicator for about 10 seconds while it evaluates your network. And then it will report how good your network is. There's also a command line version you can run on desktop macOS that does the same thing. Now you'll have noticed there, it reports the responsiveness in RPM, round trips per minute. And I'd like to explain that. Most of the time when network engineers measure latency, they measure it in milliseconds. But we realized when we were thinking about how to communicate this to end users, that milliseconds is kind of an abstract concept. A millisecond is a tiny amount of time, who cares? And we know in this webinar that every millisecond counts. And when you've got network operations that take multiple round trips, like a DNS lookup and a TCP connection and a TLS handshake and an HTTP GET, and then that HTML has a reference to some JavaScript or a style sheet, so you've got another DNS lookup for another host name. Suddenly those round trips add up to the point that the human does notice. The other aspect of milliseconds is people like metrics where bigger is better, and milliseconds goes in the wrong direction. Smaller is better. So first we considered just taking the reciprocal of the round trip time. So that gives you round trips per second. In other words, the scientific unit's hertz. And we could measure our networks in how many hertz they had, how many round trips per second. But hertz is sort of a weird sciencey sounding word. And we realized if we just multiply that by 60, then we get round trips per minute. And that has got a number of wonderful properties. On networks today, a typical round trip time gives you a RPM score that's normally 3 or 4 digits. We don't need fractions, we don't need decimal places. And coincidentally, the range is kind of familiar. It's like RPM for a car engine. 600 RPM is pretty low. You go above 8,000 or 10,000 RPM, you're risking getting up to the red line and damaging the engine. So it gives us a nice, compact integer representation that people can use to compare different network equipment they might be deciding to buy, or compare different ISPs they might be deciding to get service from. And it gives them a much more important metric to look at. So when they're on a video conference and the experience is terrible, instead of running a throughput test and saying, I've got a gigabit, what's the problem? They run an RPM test and they say, I'm only getting 12 round trips per minute. That's terrible. It's not surprising my video conference is bad. So we came up with a metric that much better reflects the actual user experience people are getting on their networks. Another important aspect of this RPM measure is we didn't look at idle latency. Almost all network speed tests back in 2020 that reported latency, they would measure the latency before they started the upload and the download test. And they did that. We talked to these various vendors that make these speed tests. The reason they did that was they said, well, the latency is terrible when you're doing a download. And we said, yes, that's the problem. Measuring latency when the network is idle is like measuring how well your car performs when it's sitting on your driveway on cinder blocks with the wheels off. Nobody cares about that. They care about how the car drives on the road when it's moving. Now, of course, good idle latency is necessary. If your idle latency is terrible, you're already doomed. But if your idle latency is good, that's the first step. What you need is good latency when the network's being used. So let's forget even caring about idle latency. It doesn't matter. And we started using this other term, which is well known in the industry, latency under load. And when we started circulating this idea within Apple to other engineers and management and executives, we got this feedback from them. We got this unspoken sentiment, which is, well, who cares about that? If the network is overloaded, obviously it's going to perform badly. That's not surprising. And we decided that the term loaded was a loaded term. It implied some unreasonable use of the network. So we realized loaded latency is not a good term. A much more useful term is working latency. It's common to think of network load as a sliding analog scale, like a dimmer switch, that load can be low or load can be high or load can be in the middle. But that's not actually the way networks work. If you take a photograph on your iPhone and text that photograph to me with iMessage, your one iPhone running one app, sending one photograph, will saturate your network to the point of packet loss, because that's its job. The job of the congestion control algorithm of a transport protocol is to send the data at the fastest possible rate. Because when you click send on an email or you send a photograph, you want it done as fast as possible. We talk about congestion control algorithms. I think a better term is rate management algorithms or throughput optimizers. There's probably better names, because the term congestion management sounds like something you only do when there's congestion, and congestion sounds like something that only happens rarely, like going to the airport on Thanksgiving Day to check in, occasional busy times of the year. And congestion is not a rare event. Congestion happens anytime you're using the network. So think about network load as an on-off. You're either sending a photograph or you're not, and there is no in between. So working latency is really crucial. And Dave talked earlier about networks with tens or hundreds of clients, and that's certainly interesting. But we're at the point now where we can't make a network work well for one client, never mind 100. So the good news is, in the couple of years since then, lots of other people have got excited about this too. Professor William Hawkins from University of Cincinnati has produced his own open source version of the responsiveness test. Ookla has added working responsiveness to their speed test app, which I'm really excited about. The Ookla speed test is one of the most well-known and popular speed test apps. And we were not sure that they would be on board with this, but we talked with them, and I was amazed the amount of support we got from the engineers, which is, yes, we know this is important, we wanted to do this, and collectively as a community, we all kind of supported each other in going to our management and saying, this is important, we should start doing this. So the tide is turning, and I'm very optimistic now that it will not be like 2015. There's a lot more visibility, and these tools are essential for both end users making buying decisions and also for management and engineers to evaluate their own work. Because when an engineer making a network product does a good job, without a tool to measure that, how do they even know whether they've done a good job? So these tools are absolutely critical. I have a call to action for everybody on this call. When you're talking to people or writing or giving presentations, let's all stop saying speed. And it's really hard to do that because it is so ingrained, even for us who should know better. We unconsciously use speed as a synonym for bandwidth or throughput. And we say, my network's fast. It's got a gigabit per second. And that is completely wrong. So I will always tell people, if I'm reviewing other people's presentations, if I see the word speed, I say right bandwidth or capacity, because almost always that's what you mean. An analogy I'll make is, if you want to move house, then renting a moving truck is the best way to move a lot of stuff quickly. The amount of cargo you can pack in a moving truck is a lot more than you can put in a two-seater sports car. That doesn't mean the truck is faster than the sports car. It has more capacity. And if your goal is to move 10 truckloads of stuff, then 10 truckloads will be quicker than 1,000 trips in the sports car. But if you just want to send a small amount of data, the sports car is the better vehicle to get there, not the big slow truck. So in other parts of life, we don't think more capacity means faster. We don't think that a big oil tanker is faster than a speedboat. We don't think that a cruise liner across the Atlantic is faster than a supersonic jet. It carries more cargo, but it's not faster. And somehow in networking, we've conflated capacity and speed as if they're the same thing, and they're not. And we have to start ourselves by stopping making that mistake and stopping perpetuating that misunderstanding by the customers, because as long as they have that misunderstanding, they will be making the wrong buying decisions. Another key point here is we talk about packet loss as if it is just an inevitable property of the network. Some networks have high packet loss, some have low packet loss. It's the fault of the network. And it's not. Almost all packet loss on today's internet connections does not come because of random cosmic rays corrupting a packet. Packet loss comes because a queue overflows. And a queue overflows because the sender was sending too fast. And if we fix that, we pretty much eliminate packet loss. You saw in the graphs I presented earlier, the first trace had enormous packet loss. And in the second trace, there was not a single packet loss. Because as soon as the queue started to build, the network told the sender to slow down using ECN. So packet loss is not just a fact of life we have to live with. It is in fact a self-inflicted wound, and we can stop doing that. Another really key thing to understand here is we can solve this. This is not like deploying IPv6 that took decades and required the whole internet to be upgraded. On any given path, there is one hop that is the slowest. And for somebody with a cable modem, if they've got gigabit cable service, typically in the downstream direction, their Wi-Fi access point is the limiting factor because it's getting less than a gigabit, unless they're sitting right on top of the access point. And if they're that close, they should plug an Ethernet cable in. So most users are not getting a gigabit on Wi-Fi. And that means their Wi-Fi access point is the bottleneck, and smart queue management in that access point will cut down the massive buffering delays. In the upstream direction, it's common to have a gig down and 35 megabits up. So in the upstream direction, the cable modem is where the queue fills up. And if the cable modem has smart queue management, which is starting to roll out with low latency DOCSIS, then fixing that one piece of hardware transforms the customer's experience. So this is really encouraging. We can deploy this incrementally, one customer at a time, and that customer gets the immediate benefit. It's not like IPv6, where it's not usable until everybody is upgraded. So we have the technology, and our challenge now is education. It is communicating to customers and engineers and their management that this is the thing they should be focusing on, not a never-ending pursuit of more and more throughput. That is not going to fix the problems. We need to focus. Not that throughput's not important. I would love more throughput. You offer me more throughput, I'm not going to say no. But throughput alone, without fixing the queuing delay, is going to result in networks that feel as bad as a slow network today, no matter how many gigabits they have. So that's my presentation, and I think we have a few minutes for questions, maybe.
Thank you very much, Stuart. That's great. We will take the questions. We are way over time, but that's not a problem, I think, because we're only at about 10% attendee drop rate, so that's not too bad for a 2-hour webinar. I think that's fine. Yes, we do have a couple of questions here. Erik Taraldsen is asking, will Apple surface the RPM tool more for end users? And are there any plans to rank ISPs or anything like that in any public way?
I don't imagine Apple is going to get into any business of playing favorites with ISPs. And that's partly why in the first release of this tool, it was in the developer settings, because we didn't want to put a tool on 1 billion iPhones that would have the customers calling their ISPs saying my RPM sucks, and the person on the phone says, what the hell is RPM? So we wanted to roll this out for developers, give the industry time to become aware of it. Thanks to Domos for organizing this webinar, because this is part of the education process, because it's not fair to spring something like that on vendors and providers when they haven't been prepared. So I can't speak to Apple future plans. You know, I'm not going to do that. But regardless of what Apple does, there are other vendors like Ookla who are adding working responsiveness to their speed tests. So at this point, it may be irrelevant whether Apple does it or not, because the widely used public speed tests are starting to report working latency. And I encourage everybody on this call, fire up Ookla speed test today and pay attention to those responsiveness numbers. And don't just look at the idle latency, look at the latency during upload and download, and don't just look at the average, look at the worst case. And I predict that probably everybody on this call is going to be very, very disappointed with the quality of their network connection. And that disappointment is the first step to fixing it. Because if we're all aware of the problem and we have a tool that we can share with other people and say, look at this, this is terrible, and product X from another company is really good, and pretty soon Consumer Reports is going to report this, and the customers are going to notice, and they're going to stop buying our product and buy product X instead because it's so much better. So that's why I'm here talking today, because we don't want to blindside the industry. We want to give everybody advance notice of this tidal wave that is about to hit them.
I think that's a great point. Really want ISPs and vendors and everyone on board with this, right? It's going to take a team effort. So blaming someone and pushing them out in the cold is not a good strategy. Absolutely. Second question is, how does RPM account for jitter?
Yes. Latency and jitter are both important. In my mind, they actually combine into a single relevant metric, which in a sense is average. You can think of it as being a bit like average latency plus jitter, or plus the 2 standard deviations. And I'll explain why that's relevant. If you plot the round trip time for any network application like this that we're doing right now, you speak, you ask a question, you pause, I hear that you finished, I answer. That round trip between you finishing and me starting affects, from your point of view, how long it took me to answer your question. And if I take too long, you're going to interrupt me because you think I haven't heard you. So measuring one-way delay is useful for network diagnostics, but for user experience, it's always the round trip that matters. And that round trip time takes some kind of distribution, like a bell curve. And with a video client such as this, the late packets are less useful. I'm not going to say they're not useful at all, because even if a video frame arrives too late to be displayed, the way modern codecs work with iframes and P frames and B frames, later frames depend on older frames. So even if a frame arrives too late to be displayed, it might still be critically important because the following frames depend on it. So there are a lot of people, when they think about video, they think that late packets are useless, throw them away. And that's a mistake, because just because they're too late to display, they might still be really important. But that aside, a frame that arrives too late to display causes a disruption in the video. Now, if the video conferencing app sets its playback delay, because every video conferencing app has some kind of playback buffer. It doesn't display every packet the moment it arrives, because it wants to play smooth video. If it sets its playback buffer at the average round trip time, that's another way of saying we've declared that 50% of the packets are too late. And effectively imposing 50% packet loss on yourself is not a way to get a good video quality. So then the question becomes, like, what packet loss are you willing to inflict on yourself and still be happy with the video quality? And my personal rule of thumb there is I want 99.9% of the packets to arrive in time to be displayed. So that equates to setting the playback buffer at the 99.9th percentile. So that's my metric for evaluating a network. It's not the mean, it's not the median, it's not even the 99th percentile, it's the 99.9th percentile. And in effect, that is mean plus some amount of jitter. They're kind of combined into one number there.
All right, yeah. The next question is quite long. What do you think about the TCP versus UDP situation? We seem to have consumed the more bandwidth solves our problems approach, natural for UDP dominant real-time streaming, as the redundancy and space complexity starts to have diminishing returns. You highlighted the TCP advantage, tapping to time complexity. They're talking about RTT multiples makes a lot of sense for timeliness. But does the ECN and AQM make UDP obsolete, as we will not throttle with retransmission, paving the way to just use TCP?
Okay, this is a really critical question, and I'll try to be very succinct in my answer, because I could probably give a whole hour-long talk just about this. Every time somebody talks about TCP versus UDP, it's like fingernail scratching on a chalkboard to me. It sets me off, because they are not comparable things. TCP is a transport protocol like QUIC or SCTP or WebRTC. These are transport protocols, and there's certain responsibilities a transport protocol does. We've all seen the OSI 7-layer model, and I won't get into like debates about like how accurate that model is, but there is a layered model. And the way modern networks work, I'm not talking about ATM or X25 or old things, but we've come to a world of packet switch networks, Ethernet, Wi-Fi. And in a packet switch network, you have a datagram layer, and that's the IP layer. And the job of the datagram layer is to deliver packets, best effort, as fast as it can, high quality, but not a cast iron guarantee your money back if the packet doesn't arrive. That's the datagram layer's responsibility. Do that well. On top of that mostly reliable layer, we build a transport protocol. And the transport protocol is responsible for putting the packets back in order if they're reordered, for eliminating duplicates, because packets can be duplicated, like on Wi-Fi. A packet might be sent, but the link layer acknowledgement is not received. Now, the sender doesn't know whether it arrived. Was the packet lost or was the ACK lost? So it'll send it again, and then you end up with the duplicate. So the transport protocol fixes reordering, it fixes duplication, it fixes packet loss by retransmission, and it manages the rate control, which is paying attention to the signals from the network that say it's going too fast. If it's going too slowly, I could email that file faster. Zoom could upscale the video quality. So if there's more capacity there, the transport protocol should make use of it. If the transport protocol is going too fast, then it needs to slow down. People have talked a lot about audio and video being isochronous streams, and other kinds of transport is bursty, or the sawtooth wave of TCP. I think that's a big mistake. I don't want my video to be isochronous. I don't want to live in a world where my video conference is a fixed 1 megabit per second. And if I've got a gigabit, it's completely unable to take advantage of that by giving me better video and audio quality. And if I have less than a megabit, the application just falls on its face and has a tantrum and refuses to work. I want applications that are adaptive to the network. And that's the job of a transport protocol. If you think about all those things I listed, UDP does none of them. What is UDP? UDP, I think this is a historical mistake of the internet design. We shouldn't have made it sound like it's a peer to TCP. We should call it IP++. UDP is the IP datagram with port numbers added. That's all it is. The port number should have been in the IP header. That was a design mistake of the IP protocol suite. And it's not inevitable. AppleTalk did not have that mistake. Xerox XNS did not have that mistake. There are other protocols where the port number is in the datagram header. But for whatever historical reasons, when they designed IP, they forgot the port numbers. And then they said, oh, we can deliver the packet to the host, but how do we know which application on the host? Well, we need port numbers. And then this little shim layer was put on top. And if you look at a normal architecture diagram of the IP stack, you've got Ethernet and Wi-Fi and cellular and all these hardware technologies at the bottom. You've got the IP waist of the hourglass in the middle. And then on top of that, you've got transport protocols. You've got TCP, UDP, SCTP. You've got all these DCCP, you've got all these other protocols. And what do they all have in common? They have a 16-bit port and 16-bit source and destination ports in them. And when you see an architecture diagram where there's a stripe of duplicated functionality across all of these protocols, that's a real red flag that should have been a common field in the header one layer below. If we designed it that way, people would not be so confused today that they think when they're designing their application that the choice between TCP and UDP, it's not. The choice is between TCP and some other transport protocol that happens to be built on top of UDP datagrams. Just like TCP is built on top of IP datagrams, some other transport protocol is built on top of UDP datagrams. And in fact, in a different world, TCP could also run over UDP datagrams, and we wouldn't have this weird mismatch. And in fact, that's what QUIC did. QUIC is a really competent, sophisticated transport protocol built by the people who learned all the lessons of TCP to make what you might call TCP version 2, but they didn't build it running directly on IP with its own port numbers. They layered it on top of UDP, which arguably TCP should have been in the first place. And if the architecture diagram looked like that, and if that's what we taught students in college, then they'd have a much clearer understanding of the challenge they face designing an application. So your choice for an application is TCP or QUIC. If you think UDP is your choice, that means you're designing your own transport protocol. And if you don't understand that, then God help the network when you deploy your application, because you've got some very amateurish homegrown transport protocol that you didn't even know was a transport protocol. And as we've seen in these presentations, how the transport protocol interacts with the signals from the network is absolutely crucial to the running of a shared cooperative network, like a packet switch network, like the internet. So to get back to the original question, how does this relate to UDP? The answer is exactly the same. Any competent transport protocol running on top of UDP has to manage its rate according to signals from the network. When a queue builds up in the network hardware device doesn't care whether it's TCP or UDP or DNS or anything. It's just IP packets. It looks at the number of IP packets in the queue and how long they've been waiting there. And if they've been waiting too long, that's called the sojourn time in CODL. If the sojourn time is too high, it sets a bit in the IP header, not in TCP, not in UDP, not anything. In the IP header, there's a bit that says this packet is suffering queuing delay. And it's up to the transport protocol at the receiving end to receive that bit, understand it, echo it back to the sender to say, hey, you got to slow down. TCP does this for you. QUIC does this for you. If you're rolling your own transport protocol, it's your job to do this. And that's one of many, many good reasons not to roll your own transport protocol, because if you've never built a transport protocol, you don't know how much work there is. And you can stumble into this mess, and you're basically reinventing TCP from 30 years ago, one bug fix at a time.
Yep, completely agree. Transport protocol is one of the things that you should not roll your own.
I said that was going to be a long answer, and I'm sorry, but I did the best I could.
No worries. Right. The next question is, any thoughts on cellular radio, where radio access network queuing is partly based on the received signal strength of the terminal and signal is particularly volatile?
This is another great example of where the whole industry, the cellular equipment makers and the operators, have been incentivized by the current speed tests. When the speed tests only measure throughput, they want to brag about who has the most gigabits per second. And they've built the networks that way. And when you read all the marketing and see presentations about 5G, they love to talk about how great their latency is. Low latency 5G, but if you measure it, it's not. And you all have these speed tests available. You have phones with 5G, so don't take my word for it. Measure the responsiveness of your 5G network. You'll be very disappointed. Now,
Totally
we can
agree.
fix this. If we stopped focusing on, I need to get my 4 gigabit headline number and say, why don't I just get a measly 500 megabits per second, but with low latency? That would be much, much better. But they won't do that until the customers start understanding that a low latency 500 megabit network is not a bad thing. That's a good thing. That's what they should be wanting. They shouldn't be complaining that they're only getting 500 megabits. They should be joyous that they're getting 6,000 RPM.
Yeah, agree. I once measured the 5G network in central London using the Ookla speed test on my phone, and I had, the worst case was 12 seconds of latency.
In today's world of gigabit networks and gigahertz process and gigabytes of RAM, the idea that we're measuring anything in whole seconds is completely insane. One of the analogies I make for those of us who are old enough to remember spinning hard disks before SSDs, hard disks were always sold with a throughput and a seek time. Every hard disk quoted at seek time because people knew that seek time was important. And somehow when we built networks, we forgot about the seek time as being important.
Yeah. All right. We're about half an hour over time now. So I think there are a couple more questions, but I don't think we'll have time for those, unfortunately. So with that, thank you very much for the talk, Stuart.
Thank you.
And just to wrap up, today has been about what latency is and why latency matters. And tomorrow we'll be back to discuss how big the problem is in the internet and what's being done to fix it. So we'll hear from people with experience measuring latency at large scale and from people working on solving the problem from several different angles. So with that, thank you very much to all of our speakers. I'd call for applause, but that doesn't work over Zoom. So we'll have to imagine your own applause. But see you guys tomorrow, and I hope as many attendees show up then as well. Goodbye.
Bye-bye, everyone.